And we're back. Hey, we're having an after show for the Dr. Lawrence Krauss discussion that we just had on Non Sequitur. We do have actually Lawrence with us, but not that one, unfortunately. But we have a different Lawrence, Lawrence from Milwaukee Atheist. And if that's not good enough for you, oh well. But I happen to like Lawrence, and I'm going to take what I can get at this point. So he's here. He's actually be talking about the book Universe of Nothing. I'm going to be talking about a Universe of Nothing a little bit. People had asked questions that maybe between the two of us we might be able to answer because we both read the book. There were some physics questions that were brought up that I think is the most interesting part of the book. People seem to have, when they're talking about his book, they seem to be talking about a completely different thing than what he wrote. And I brought that up with Dr. Krauss. I was like, when people discuss nothing, there seems to be a huge equivocation issue. And even then, if they do understand what they mean by nothing, the physics is very difficult to wrap your head around. That you have this metastate of a false vacuum. You have this ubiquitous 0-point energy. You have this conditions of negative energy. You have conditions of localized decrease in entropy. They're not easy to wrap your head around. And so his book, I think, gives a really good indicator of the science overall. But if you don't understand some of the terminology he's using, it's going to be quite difficult. Like some of the things he brought up was like the cosmic horizon problem, the monopole problem, and there's a couple other issues that he brought. But those are some of the big ones, like the cosmic horizon problem is something he doesn't much talk about, but I think it's a big issue about why we know the Big Bang happened, because of inflation. Why we're looking at the cosmic background radiation going, hey, look at this, it's flat. And what does that actually mean? What does the resolution of these hot and cold spots mean in that data? For the Planck or the what is it, the WIMP data? There's Planck, there's WMP, and I think there's one other satellite out there that gives us some data. But anyways, let me go to my live chat here, see who's out there real quick. I got Jim in here also. Jim from Atheist Republic. Yes, Handsome Jim, we called him. Yes.
Hello, everybody.
That's what they call you, Handsome Jim.
Who's they?
Koisa, he says, oh, Handsome Jim Majors is here too.
Oh, hey, Koisa, what's up?
Yeah, it wasn't about Steve or Lawrence. It was all about Jim. That's okay.
Well, he's obviously not blind.
Clearly not. Yeah, Jim's pretty hot.
No, I'm beating my own horn.
You sweet heathen. Jim is the one and only hall pass you get.
Oh my gosh, sweet heathen. Oh
yeah.
Steve,
I will
the only
slice
person.
You. I will slice you. So just be careful.
That is the only person that I would probably fight you for, Steve.
Yeah. Well, you know what? I don't blame you for that, so I'll let you survive.
But I would take you to Applebee's afterwards just to show you that there's no hard feelings.
There you go. You know what? I'm okay with that. You give me the full detail and notes too while you're at it. That'd be great.
Right on.
I might learn something from you. Yeah. Oh my goodness, I have a really horrible hair day. But yeah, it's okay. Anyways, let's get back on topic here before we embarrass Sweet Heathen any more than we already have, and she never talks to either one of us. So the book, Universe of Nothing. There's a couple things that it's important to remember on the Universe of Nothing. That nothing he's talking about is not philosophical nothing. It's not ex nihilo. It is the absence of space, time, and matter. And in some cases, you can even argue fields. But what happens is when we predicted that the universe started from this very hot, dense state, and again, this is where Lawrence is going to jump in and hopefully agree or disagree and kind of add to this. But the universe in this hot, opaque state was such that there wasn't any combining of electrons and protons to form atoms. Hydrogen didn't even exist at this point. So what happened was, as the universe cooled down, all these photons that were being absorbed and reabsorbed and moved around and just moved between these particles, the electrons and protons, they couldn't go anywhere. It was like trying to look through a wall. You can't see through a wall, right? Because it's opaque. It's not transparent. And so it wasn't until the universe was able to be cooled down where the protons and electrons combined, it's called the recombination period, that when that happened, all of a sudden, all the photons that were trapped in there from this very hot state, they sped out. They went poof. And that, what we see now, is the residual light from that. So this was about 3,000 degrees Kelvin when this happened. We predicted, based upon the modeling, that if there was this happening, this recombination happening, such that light would go from this very hot, opaque state to where it is now over a period of 13.7 billion years, then what temperature would it be at? And the initial things they predicted were a little bit high. I think they were around 3 to 5 Kelvin or even a little bit higher, but then they kind of narrowed it down. And they found out that it was around 2.7 Kelvin. And they accidentally discovered it by a radio antenna back in 1964, I believe. So this was a predictive model. This was actually saying that, hey, if the Big Bang is the case, if there was a hot, dense, opaque state, and 13 billion years later, what would it look like? What would we expect to see as far as the temperature? And sure enough, the temperature we arrive at was 2.725 Kelvin, which was almost right on the nose what they predicted, around 3 Kelvin, give or take.
Right.
That's not coincidence.
But that's only going back to a certain point. I mean, we can't go back to the singularity, but we know within a few seconds of the Big Bang that's what temperatures we reach.
Yeah. The thing is with it, we can't look past that point because light was basically trapped at that point. So that's
Right.
that's the furthest back we can ever see anything for that very reason.
Yeah, it's called the CMB is just the last scattering surface.
Correct.
Right. Yeah, I just want to bring that up for the people watching.
Yeah, as a matter of fact, the last scattering surface, the discrepancies we see in the CMB, right? We see hot and cold areas. And we don't mean like really hot and really cold. We're talking about a very small degree of difference, right? But there's a couple of things that are encoded in that. One, it encoded the quantum fluctuations at the state that it was during the initial conditions of the universe in that phase transition. So there's basically the way it's explained, a phase transition is something going from like solid to liquid or liquid to gas, right? These are called latent heat and vaporization. So the amount of energy going into something, for example, if I want to melt an ice cube, I'm not changing the temperature of the ice cube at a certain point. What I'm doing is I'm changing the phase state. I'm changing it from a solid to a liquid, right? I'm breaking the bond. Right. So all the energy going in that system,
changing the molecular structure.
You're breaking the molecular structure of the intermolecular bonding, right? You're not breaking the water molecules, but you're breaking the intermolecular forces. And that energy is going into doing that, not raising the temperature. That is called latent heat of vaporization from one phase to another, or for fusion to go to ice. But that's a phase transition. So these quantum fluctuations that we normally can never see, they happen very quickly. They're within Planck's time. They have posited that if there was a phase transition or very early on before the recombination period, it would carry over till now. And so the variations we're seeing is quite literally frozen quantum fluctuations having an effect on that what you would call the last surface. What is it? I forget the exact name. The last surface.
Last scattering surface.
Last scattering surface. And also, it also tells us if the Earth, the universe is flat, whether it's closed or whether it's open. Somebody had asked that question as well. They've determined the universe is flat locally to a degree about 6 sigma, which is pretty freaking flat.
Right. But I mean, flat. The Earth is flat. I mean, through context, through where we are. I mean, from what we.
No, it doesn't mean that kind of flat.
Hold on.
Well, it kind of does in a way, because the universe is only flat in certain areas.
No,
because Okay, so tell me if I'm wrong here, though. Like when the universe expanded, it expanded. Hang on, damn it! It expanded in tendrils, right? It expanded out in tendrils, but each of these tendrils are flat upon which different planes, right? Like different flat surfaces.
What is this? Is this like the fly spaghetti monster?
I don't know.
No, this might just be a misunderstanding.
All right, let me see if I can explain. I'm going to bring
a student.
Yeah. Let me see if I can hopefully, and I got Ben in here who knows physics, and I got Nick who's a philosopher and knows mainly about physics. But
it's good because you got an idiot in here.
No, it's not your purview. Okay, don't be so hard on yourself. Not mine either. But I read these things. But when we're talking about flatness, we're talking about local geometry. And so if we have, like, for example, a triangle in Euclidean space, it could be greater or less than 180 degrees, but in non-Euclidean, it's flat. So what we're talking about more is the light path through a specific part of the universe. We're saying that light will travel in a geodesic straight line in a flat universe. It subtends from the eye, from where we're at, to about 300,000 light years. This is the granularity of the CMB we're seeing, subtending from where we're looking at to 1 degree, which is about 300,000 light years. And we're looking at these different discontinuities called homogeneity, lack of homogeneity in the quantum, in the cosmic event horizon. God damn it, cosmic microwave background radiation, which is the frozen version of the quantum fluctuations. Yeah, this is like a mouthful to say with this stuff, right? I mean, this
So
is really
okay,
cool.
I think maybe I can.
Maybe you can take it from there.
Yeah. Okay. So what Steve said was right. It's about how light travels. So in an open universe, picture it like kind of shaped like a saddle. The if we were to have like this huge like imaginary triangle across the universe, the angles would be less than 180 degrees. We would see less stuff. In an open universe, sorry, in a closed universe, we would see more stuff. And the ratios that we find are consistent with the flat universe, where light travels directly, and we don't see more than we should mathematically.
Exactly. Yeah, I would totally agree with that. Ben, what do you think of that?
Yeah, that's, as I understand how I've only done a little bit of cosmological research with regards to my physics knowledge. I know I took modern physics in college. I know about, like literally when I was taking this modern physics class is like that semester is when they discovered the gravitational waves, and my physics professor took the entire day out of the curriculum to say, "Hey, they just discovered gravitational waves from this interferometer that we were talking about from the beginning of the semester. And you guys know how that works now." And we were able to go through, and he went through all the math and stuff, and it was a really, really unique phenomenon.
How huge was that? But I mean, look, what people don't realize, gravitational waves were posited way early on, right?
100 years ago. Yeah.
Yeah. Well, I mean, it was like a necessary condition for relativity. And a lot of scientists still thought, though, kind of would be never be able to detect them, right? And all of a sudden, when we have the LIGO, and we not only, I mean, if you look at the data, right? If you look at what was supposed to be hypothesized of what the data would look like if you had these black holes combined, and we've seen other waveforms just too. We've seen waveforms for neutron stars, colliding. We've seen other astronomical bodies, but those are very low energy. It's hard to imagine, but 2 neutron stars ain't nothing compared to 2 supermassive black holes, right? Yep. So when you have the one that we discovered, and you can correct me if I'm wrong, I think one was about, I don't know, there was some in the range of 60, give or take, solar masses. With it, I don't remember the exact value, but I remember there was 3 solar masses that was converted directly from mass into energy, which is gargantuan, and that was enough gravitational wave to be detected by LIGO. And that's, I think, is even on the smaller end of what we're trying to hope to detect when we put this laser interferometer in space. Yep. Right.
How does that affect Einstein's equation? E equals mc squared. I mean, if energy is mass, I mean.
Well, that's just a relationship. Energy and mass, that's just a relationship. Like, I didn't get into this with Krauss because I probably would have gotten too deep and would have gone a lot more into philosophy than I would have liked to. But I mean, you could actually take a reductionist approach and say, look, mass isn't even a thing. Mass is condensed energy. All that exists is fields. And because, I mean, if you think about it from a mereological nihilist point of view, objects don't exist, right? This cup, by the way, which probably is because of my green screen.
It's a perfect example. Doesn't exist.
Doesn't exist. What this is just a rearrangement of primitives, which would be your atoms. But the object itself is just a collection of them. It doesn't have any real form except that we as humans give it form. And then you have right, when I'm hitting this, right, I cannot be in the same space at the same time. There's something called Pauli's exclusion principle that works on fermions. And fermions don't like to be in the same place at the same time. They can't be. It's a physical thing of the universe for some reason. Pauli's exclusion.
Yeah, the waves can't like.
They can't exist in the same space.
Yeah.
Now bosons can, but fermions can't because they have certain wave function equations, the Dirac functions that they have to abide by. Bosons don't. They're called Bose-Einstein's
Bose-Einstein condensate.
Well, condensate is a helium version of it that has to operate on that. But yeah, I'm pulling this deep here, guys. So I didn't expect to go into this. But it's a fact that we can't be in the same place at the same time. So we have that feeling that we're touching matter. But if you really think about it, all that exists is just forces. Matter's not really a thing in that way. And I didn't want to talk about a physicist like that because you probably would agree in the long run. But it would have been a very philosophical question. Does matter exist? What does it mean to even exist at this point? If we're just a bunch of fields, that's a
that is pretty much what it boils down to, just a bunch of fields.
It really is.
Well, if the universe is flat,
field and fermion field and whatever.
If the universe is flat though, and it's not like a torus, or it's not like in a closed any kind of three-dimensional spherical object that we would normally see. If it's truly flat, then that means that at some point the expansion is going to end. Knowing that expansion is slowing down, we know at some point there's going to be an end to it, right? On the flat universe.
Actually,
the expansion is not slowing down.
Yeah, actually, have a problem with that. It's actually accelerating.
But wouldn't it slow down and stop at some point on the flat model?
No, because
it should, but it's not, and that's what that's a big problem.
Yeah, let me turn to Nick here in a second. By the way, Nick, good seeing you again. But if you got to think about it this way, if the universe was negatively curved, that would mean that it is expanding, but it's such that it will eventually slow down and crunch itself. It'll come back, right? That's not going to happen. If it was positive, if it was a positive curvature, it would just infinitely go on forever. Right.
But which would agree with the idea that it's not slowing down, that it's not stopping. Right.
But it is accelerating. That's the problem. Not only is it not slowing down, but we discovered it's actually speeding up. That's the whole point of dark energy, to explain that phenomenon.
Yep.
Well, to explain it doesn't explain it. We got no idea.
In order for it to speed up, though, wouldn't there have to be an increase in energy or an increase in matter?
Yeah. Well, there is an increase in energy. This actually goes to the heart of the question that I asked Dr. Krauss, and people may have understood it, but when you have an expanding volume, the total energy of that system is going to go up when the density of the energy is constant. So you're getting literally energy from nothing. It's called Gould called it the free lunch. Is the ultimate free lunch. You're literally just getting energy out of absolute nothing. It's not a violation of the law of conservation of energy because it's offset by the negative pressure. But it's still the total energy of the universe is net zero, and so you're not gaining anything net, but you are gaining the fact that you have this energy, total energy, seemingly coming out of nothing because the universe is expanding and accelerating.
So is it possible? And keep in mind, I'm a physicist. Nobody. I know jack shit about physicists, about physics. In fact, some of this is really kind of getting my brain to turning. But I'm wondering if there couldn't be a leak. From where everything originated from where the Big Bang is, like if all the energy was not released at once, but rather eked out, slowly after the initial explosion.
No, because the CSB, first of all, the cosmic background radiation is ubiquitous. I mean, it's close to as we can probably imagine to being homogeneous. I mean, the homogeneity of
it's consistent.
Right. But there is discrepancy in it due to quantum fluctuations or in the early primordial state. But what you're thinking of, there is something similar to that, and I don't know if one of you guys might want to touch on it, but it's called dark flow. Ever heard of that term?
Oof.
Okay.
Dark flow. Dark flow is the impingement of theoretically another universe that's spatial temporally isolated to ours, but can have some kind of causal relationship as far as influence. It's theoretical. I have no idea whether it exists or not, but they think that certain things they posit, like the great attractor, might be that. They think that certain abnormalities that they see in various places where you have like great voids, that might be something along dark flow.
There was actually a really good Twitter post that I saw from some physicist that I found in my feed who was describing the fall of water. Like if you ever go to like a community pool or something, and they have those weird mushroom dome looking things, and they like spout water at the top.
Mm-hmm.
He used that with a really awesome analogy for how this like how the cosmic background radiation and how the remnants that we've seen from the Big Bang actually like kind of look the way they do through this analogy of this falling water thing. I'll post it in the chat so you can see, Jim. It made perfect sense to me, and before I saw this, it was a very complicated thing to explain that inhomogeneity of space, or of the cosmic background radiation, and how space-time's expansion has essentially developed that naturally as a result of physics. And
so it explains the
so
answer.
cool. Yeah, it explains the anisotropy of the entire cosmic background radiation.
John asks why. He says, can you briefly explain the net energy, why the energy is net zero? Sure, because if it wasn't, because we know the Earth, we know the universe is flat now, at least local geometry. If it wasn't, we would see more positive or negative curvature, right? So we know that there's a balance. And what we're looking at is Einstein's equations. And Einstein's equations basically say that on one side of the equation, it has this mass. Okay, so mass has a positive effect on the curvature of space. And on the other side, we have the actual negative curvature of space. So these have to cancel out. So the whole system has a net zero energy to it. Because if it didn't, we would definitely see the space-time not be as flat as it is. We would see it either be in like a saddle shape, which would be negative, or positive curvature, which would be more like a sphere.
So in just the few little physics things that I've learned, this is kind of my theory. And since there's so many people here who are, we're talking about it, I might as well throw it out there. But I've often entertained the idea that the Big Bang resulted as a result of a supersaturated black hole that just literally exploded out the other end. Is there any physics evidence
back
for
in the day?
that?
Paul Davies posited something similar to that.
Mm-hmm.
Okay,
but that was back in
Paul Davies.
Yeah, Paul Davies.
Well, that was originally the oscillating theory of the universe was the biggie. When we first thought that, is my mic loud enough? Or
yeah, you're good. You're good.
Yeah. Okay.
Yeah.
The oscillating theory of the universe was a big one for a little while, where before we realized that the universe was actually accelerating, but we thought that perhaps what was happening was the universe would expand, eventually it would slow down, and then the gravity would cause it to reverse, come back until you got a big crunch, the opposite of a Big Bang. It would all, boom, collapse. Eventually the mass gets so huge, bam, explode again, and then we just get the oscillating, and that was it, oscillating theory of the universe, and that just kept going and going and going.
So it's just like a super compression of matter down to quantum energy, and when it hits that quantum energy level, it releases.
They call it the omega point. It would reach an omega point, and then it would collapse upon itself.
No, that's not what happens. I was a huge fan of that theory. That was a great theory until we discovered that not only the big question as to whether or not that was what was happening was there enough mass in the universe to have enough gravity that the universe would eventually collapse in on itself, or was the mass sufficient that it would reach escape velocity and eventually the universe would just keep expanding forever? Not only was it neither of those, there is some unknown energy. We have not been able to find it. We got no clue what it is, but there is an unknown energy acting on the universe that is causing it to accelerate. Because we don't know what it is.
Dark energy.
We call it dark energy. We don't know what it is.
It's a placeholder.
Dark energy is the name for it.
Look, it's a cosmological constant, basically.
It's the fudge factor. It's the X. I mean, it's the X. We put it in. We haven't. Yeah, Steve is like, he's like, it's the ontological thing. We call it dark energy because we haven't a clue what it is. Right. Nobody can find it. There's no way to act on it. We don't know what it is, but we know it's there because it's causing it to expand faster.
Something has to cause it to expand, right?
Yeah.
Ben, that Twitter post is really helpful. I just read through it, and that makes a lot of sense. And that really, because I'm visualizing the same thing in my head. And when I said that, it expands into different layers of flat planes or whatever. Like that's kind of what I was envisioning. But I guess I was just thinking of it in a closed model.
it's really really hard to visualize, and until I actually saw that Twitter post, to me it's because you're thinking about this entirely in like not only just like you kind of think about it like there was what was it? There was a really great show that I used to watch. It was either on Discovery or Science or something, where their introductory like animation was like maybe it was. I think maybe it was with Mike Kaku. I can't remember, but it was some universe show, and their initial thing was just a blowing up sphere. Yeah, yeah. It was. I think it had him on it all the time, but love the guy.
But isn't there still a lot of ambiguity in the different models though, as far as whether it's flat or closed or open?
One is Lambda CDM. That's the most prevalent model. But
how prevalent is it though? Like
I think right now the only debate is between whether it's flat or slightly open.
Yeah.
Somebody had asked about the horizon problem. We kind of passed that up a little bit. Sorry about that. Real quickly, because we passed over that. The horizon problem is kind of this. If the universe was in this dense hot state at one time, there should be absolutely no reason that it's at thermal equilibrium across its system, because it's too far away from each other. Information, light, matter can only travel less than c. Okay, so it doesn't have any possibility, just based upon the Big Bang, to why there's so much homogeneity in the cosmic background radiation. It shouldn't be. Even the fundamental constants shouldn't be the same everywhere. It has not had time for causality from one point of the universe in one direction to the other points in the other direction to have thermal equilibrium at the early state. It should not be. But the way they get around that is they posit something called inflation. So inflation kind of resolves that problem, because at that time, space-time is moving faster than the speed of light, because relativity says nothing in space can travel faster than the speed of light. It doesn't say space itself you can go any speed it wants.
Right. So, yeah, I've seen the balloon analogy where they mark 2 points on it with a Sharpie and then inflate it.
Yep.
Yeah. Similar. Inflation just refers to like,
inflation just refers to like a really fast period of that.
Right. But it's all relative though, right? Like in the expansion in that model, it's relative.
Relative to what?
Like relative to whatever point you're at. I mean,
there was nothing there. This happened so quickly. Inflation happened so quickly that boom, it was just like a universe.
Right. Well, but
if I'm getting it right, I could be getting the numbers a little bit wrong. It went from the size of like an atom to the size of a golf ball in like 10 to the negative 32 seconds.
Right.
Like that's incredibly
-43, -32, and then by -37, I think, or let's put it this way: by the time that you had gluons and forming into and quarks forming into protons and neutrons, it already expanded. I don't even know the factor, but it was quite big. You might have to look up the numbers. But at that time, when you had actual particles being formed, it was huge. It was huge.
What do you think about the theory about the negatively curved universe, like being open, like it having too little energy to stop expanding?
Well, we know that's not the case because of the cosmological constant is increasing. We know that Hubble's constant is increasing.
But is that not possible on that model? I think they call it the saddle model.
The saddle model would be negative curvature. Omega next.
Right.
When omega is less than 1.
Right. Well, it's a negative curvature, but it's on an open model. But it wouldn't be possible there.
I would have no idea. I mean, I don't know Hilbert spaces that well.
Okay.
I don't know.
Fair enough.
Oh, just something quick. I posted a link in our side chat here to my video about the horizon problem. I don't know if I can. I don't know if it shows up in the live chat.
Awesome.
Yeah. Where is Landon? I will tell you this. I had a conversation the other day about this with somebody, and maybe you guys might be interested. Lawrence, are you familiar with the holographic principle?
Yeah, a little bit.
Do you want to try to explain it, or
I'm thinking of something else. I think I'm thinking of simulation.
Not simulation. Okay, the holographic principle is an actual pretty cool thing in science, and what it is, it's saying that all the universe, all the three-dimensional things that we know exist, is encoded informational wise on the observable event horizon boundary in 2 dimensions. these are called little qubits on the two-dimensional membrane. So it literally is saying that if you want to describe the entire state of the system, the entire universe, that information is encoded on the surface area of the event horizon of the observable universe. Now, how cool is that? And that's something that comes out of black hole theory.
So apparently somebody says,
yeah, okay, now I'm starting to remember this. Yeah, because like I think I saw something about black holes, like getting like the imprint of the thing coming in, something like that.
Yeah, it has. The reason they have that is because the information paradox. Because information was not supposed to be destroyed. There's three main things for a black hole. You have your angular momentum, you have your mass, and then you have your charge. But information going into there was in quantum level must be conserved. Quantum information cannot be destroyed. So where to go? It's actually encoded on the event horizon of that black hole.
So how many black holes will it take for us to make a like 64-bit quantum black hole computer?
It depends on how big the black holes are.
Well, they have a, what is it? How many quantum bit is the one that's you can actually go and you can watch it in real time? You can actually program it yourself over the internet. Was it 6 quantum bit or something? 8 quantum bit?
I think it was either 8 or 16. I want to say.
Have you seen that? You literally can go online now.
Really?
Yes, you can go online and you put you in a queue and you can program. If you understand quantum programming, which I don't, but if you understand quantum programming, you can go program a quantum computer and it'll do it for you.
We are going to be carrying around megabits of quantum computing in our pockets in the next 20 years.
I have no idea how quantum computer. I tried to learn. It was way beyond my pay grade. I don't get
this is a little bit into my wheelhouse because as a materials person, I have been wanting quantum computing to be a thing forever. There's I don't know all of the advances that they've made with regards to what they're currently making the quantum computers with, but from what I remember way back when, and I might be confusing this with some of the varistor technologies that they were coming up with at the same time.
Variable transistors?
Yeah. But not varistors, memristors.
Oh,
so a memristor is a memory-dependent resistor that is aware of what resistor value it has been in the past, such that it can change its future value for processing data differently. They were trying to use rutile, titanium dioxide, which has a tetragonal phase that has, with a certain amount of oxygen depreciation, allows for it to snake in oxygens in such a way that it will fill in certain oxygen sites, but not others, in a way that you can manipulate to produce that memory resistance state, and it is
awesome.
Wow.
So cool.
I don't know anything about that.
It is amazing how much of a step quantum computing is from just zeros and ones. Like it is just amazing.
No, it's 0 and 1, and then so you have a superposition where you have both.
Yeah.
Okay, Steve, you're right.
Yeah. but superposition again. This goes back to what we said earlier. Fermions don't have that, right? You can't have fermions in the same position, but you can have a boson can. But what we do is we use the orbitals. The orbitals are such that in an electron state that you have spin up, spin down, but they can still okay. I'm trying to think how does this work for electrons for superimposing? I'm trying to remember this because they are fermions. They have to abide by the Pauli exclusion principle.
You have filled orbitals of up and down. You have to have the pair.
So you have a pair. So like the s orbital. Let's look at the s orbital. So you have one up and one down.
That's a filled orbital right there.
But how they get in superposition?
I don't know.
Yeah, I'm having to think about this now. I don't know. I don't know anything about quantum computing. I'm telling you guys.
Sorry, Ben. Go ahead.
In terms of the actual like macroscopic, because that what we're talking about when it comes to qubits for quantum computing, as I understand it from the materials perspective, is that you're not dealing with actual quantum states. You're dealing with the abstract quantum state of superposition with regards to this is neither a 0 nor a 1. It is a both, or it is a neither.
Entanglement.
Yeah. So,
it's entangled, but they're not superposed in the same location. So they're just entangled, which makes sense. Okay, it's obviously one's upstairs, spin down. It has to be.
Yeah, it's not a physical entanglement. It is an abstract entanglement for the purposes of programming it. I'm pretty sure, but
that makes sense.
I'm probably wrong about that. But like the principle of quantum computing is different from literal quantum physics.
Right.
Okay. That makes sense.
Have you heard about Purdue's research with nanoribbons?
Nanoribbons of what kind?
Like nanotubules?
No, nanoribbons in terms of quantum computing. I don't know if that term is used elsewhere, but they in Purdue University they've developed this thing called nanoribbons, and it has something to do with the way that it conducts the charge to the qubits or qubits, however you say it.
Yeah, equipment.
And
nanotubules.
qubits, okay, and instead of running it through, they run them. It's like a topical. It's like a surface.
Topological. Yeah.
Form. Yeah. It's a topological conductor. That's what it is.
Yeah, because you don't have the losses.
Right, and what it does is it because like one of the problems that we've had with qubits and with quantum computing is the qubits are very sensitive and they're not immune to a lot of things like noise, light. I mean, a whole bunch of different things can affect the way that they act. Yeah, incoherence. I'm sure I've got that going on in my own little quantum computer.
Decoherence.
Oh, decoherence. Yeah. See what I mean?
Quantum decoherence is a bad thing if you're trying to keep information.
But what the nanoribbons do, according to the research, which I actually read earlier today in prep for Krauss's thing, I was hoping I would be able to talk to him about it. But what it does basically is it extends the life of the qubits by increasing their immunology to these variables.
Yeah,
that makes sense.
Yeah,
because quantum computing, you don't want to lose that state, right? You
got to lose the state, you lose the data,
and that's why it has to be kept very, very cold. These are cryogenetics things. This is why I'm wondering how quantum computing at room temperature is going to work. If right now we have to keep these things in liquid nitrogen to keep them cool, so you don't have decoherence. How does quantum computing work at the at like normal ambient temperature?
Material innovation is all I can say.
Yeah,
I don't know. Water cooling seems to fix everything.
There's a lot of things that go into it. It's not just the topological current or the topological conductor, but it also has lots to do with the insulation of the qubits and protecting them from the. I mean, because you got to think about the level of current that you're running through these things. I mean, when you're comparing size to energy output.
Oh, it's liquid helium, not nitrogen. You're right. Thank you. Whatever. It's still cold.
Yeah.
Cold is cold after a point.
You know, and I think that if I remember correctly, somebody can look it up. I think helium-3 is like one of the very few, if known, macro. Is it fermions or fermion? Because most fermions have a spin of 1/2, right? Leptons have a spin of 1/2, and fermions are a type of lepton. But fermions usually are only seem to be like electrons and protons. But there are certain things like a helium-3. I think, if I'm not mistaken, is actually considered to be a fermion. I think it's like the only exception to that rule where you have all fermions or leptons, but it can be bosons, can be fermions too, if I remember correctly. But somebody can look into that. Particle physics, going way back when. But I
helium-3.
Yeah, I love particle physics, but I don't know anything about what you're talking about.
Well, you have fermions, leptons. They both have a spin of 1/2. You have bosons. You have mesons, pions, muons. These are all just configurations. For I hate saying this word. I call it hadron, but it's hot.
It's hadron.
Hadron.
Yeah, hadron.
But I mean,
helium-3 R. I hate saying.
Well, helium-3 is a helion just because of the state of the nucleus.
Hadron. It's pronounced hadron, by the way.
Oh, it is, isn't it?
Yeah, no, it's pronounced hadron. That's why I always screw it up, because
it's the hadron.
Yeah. It's pronounced hadron.
If you have a thick enough accent, anything is pronounced however you want it, Steve.
Yeah, no. All my life I grew up. I like particle physics. I always called it hadron, but I knew that it wasn't. I was always mispronouncing it. It's hadron.
I noticed something that you had typed earlier in a comment a few days ago, and it auto-corrected to hadron or hadron, however you say it. And I wanted to comment so bad, like only a nerd would have his word auto-corrected to hadron.
Has anyone seen Neil deGrasse Tyson live?
No.
Yes.
Yes.
In person.
He's hilarious live. He's great, but he does this thing. He's hilarious, but he did this one thing, and it's just because Krauss mentioned it. He does this thing. He does a slideshow. He does all these things, and he talks about also geeks who brought their girlfriends who are sitting there going. He goes, "I know a lot of this is going to be over your head. I'm going to try to bring it down to your level." He goes, "What I want to do is I want to bring up now. It's just going to be one word on a slide. He goes, some of you aren't going to get it, but this whole place is going to go wild. One word, this whole place is going to go wild. Nothing I can do about it. Brings up the next slide. It's Pluto. And everybody goes crazy. Everybody goes crazy.
You know,
but
it was still, it's even if it got downgraded, it was still a dwarf planet.
Yeah, but the whole idea behind the classification of what is a planet, and I think what was it in the end, it had to do with the shape of its orbit, like because it was too elliptical or something like that.
It was,
in order to be a planet,
small
there's a certain conditions to be a planet, and I
right.
forget.
It has to operate. It has to operate within a certain. It has to orbit within a certain degree of ellipse or whatever.
They're bringing it back. That he's been overruled now. It's going to come back to a planet.
Good. I hope they burned him at the stake.
Heathens.
That's heresy.
Well, you know it's CGI because I mean now Disney actually put Pluto's face on Pluto just as a little.
I mean, clearly, if the moon's CGI, Pluto's definitely CGI.
Clearly.
No, it wasn't Pluto the dog. That was a dragon, right?
I don't know. I get them all. My pareidolia sucks, so I just see boobs everywhere. That's all. It's weird for me.
Pluto's boobs. Yeah. Oh no, Ultima Thule. Yeah, that's just a pair of boobs.
It's all boobs.
I see boobs everywhere, and then I wake up broke. I don't know what's going on.
Yeah, that's called loneliness.
Oh yeah, I'm definitely suffering.
Hey Jim.
Hey Christopher, I didn't see you there, buddy.
Your porn. What's wrong with you?
Christopher snuck
I know,
in.
right? I could just go and watch your video.
By the way, I didn't finish it, but I watched a good chunk of it, I guess. But your discussion with Aaron was really good, dude.
Really Thanks.
Good. It really was.
Yeah. You know your shit. I'll give you that.
Thanks.
Yeah. Yeah. I respect you for holding one of your idols' feet to the fire for as little as you did. You made them slightly warm. You didn't roast them like I wanted you to, but you did well.
Put this up. I haven't seen this. Do you want to put this up on the group chat, or is there a link to this?
Oh, sure. Let me grab it real quick.
All right.
Terry, you wanted to come in. What say you on all this, Terry? How you been?
Well, I've been following Neil deGrasse for a while now, and Krauss as well. That's where I started off my interest in YouTube and everything. That's what led me to the flat Earth subject as well. So a lot of this information that they give out is very very helpful.
I think it is.
I'm learning.
I think science communicators are important. Now, granted, I'm digging deep for a lot of this stuff, and if an actual physicist was probably listening to this, they're going, "Yeah, you're mostly right." Good for government work, but yeah, I mean, I'm definitely not authorities on any of this. But I find it to be a fascinating topic. I think that people that can communicate good science, like Dr. Krauss and Neil deGrasse Tyson, they're rare breeds, and to get them on to have their caliber is just. I never thought we would ever reach that level in the Great Debate Community or Non Sequitur Show where it would be like almost commonplace to have, hey, look, we got Neil deGrasse on. Okay, because hopefully we might have him because we actually were supposed to be able to hang out with him last year, or at least I was. Atheist Emperor was going to arrange that. So, but now it's like, oh, look at we got Neil, we got Lawrence Krauss come on, we got Hugh Ross come on, we have Jim Majors come on. Not that anybody cares, but we got some, pretty.
Even Bill Nye. I listened to Bill Nye too.
The science guy?
If you guys got Bill Nye, oh my god!
See, the problem with Bill is we've really tried, but the thing with Bill is he is so protective of his image, and he has to do due diligence to even appear anywhere, much more than I've ever seen anybody else. So we just kind of said, whatever.
Well, I think of the scientists that are out there, the ones that are in the media. It is a good representation of how science should be taught in its fundamental levels through schooling and education, because people are just not coming through interested in science. You sit in the classroom and look at the blackboard and whatever the teacher puts up there, and kids are sitting in the back of the classroom going, well, what's this going on about? This is not interested in me. And they leave high school and go to university and follow other paths and careers, and a lot of them would have had the intellect to have gone further forward and gone to do a science degree of some sort.
Absolutely. I didn't get much out of high school. I learned more on my own.
Yeah, same.
Yeah, Sam. Yeah. So just out of curiosity, I know that we're talking about a universe from nothing, but have you guys read Krauss's most recent book?
I have not.
No, I have
Greatest
not. Well,
story ever.
which one is it?
Greatest story ever told so far.
No, I haven't. What is it about?
I mean, it's basically just like the history of like our scientific discoveries and our endeavors and stuff like that. It's
Wow.
it's
I hope.
it is
I really hope he gives the Catholic Church their due. So they don't.
Well, he actually gives a history in Universe of Nothing. He kind of goes into the not very much. He just very tertiary, But all you really need to know, I mean, in a nutshell, right? The timeline for Lemaitre and from Guth and a few other notable scientists that said, okay, let's pause. There's some of them I've never even heard of. I mean, he mentioned a few scientists in there that I had never heard of before, and I was like, okay, this guy discovered this. I had no idea. Don't even know who he is.
So I didn't catch the first part of it, but did somebody get to ask Lawrence, or did he explain what nothing is?
Well, nothing is something.
He describes nothing as as no space, no time, no matter. But
Just
I think there has to
quantum
be, there has to be obviously an energy density there. So
what do you think about like the description where somebody says that it's just negative energy and positive energy, that there's not an equal how do they put it? Like they're not balanced.
Well, they are balanced in the field equation. That's what's cool about it.
I'm trying to think of the way the person put it, but he said basically that quantum energy is the state of positive energy and negative energy not being equal or something. Or
well, you talk about the Heisenberg uncertainty principle.
It's possible.
I had mentioned to him there's something called a Hamiltonian, and Hamiltonian is the total energy of the system based on your potential energy or kinetic energy, and the quantum fluctuations for the way that we know that you can never know the exact position of a particle at any given time and the exact momentum. It's a trade-off, right? So you know one, you don't know the other. So anytime we measure for any kind of definite period of time and we're measuring a particle's momentum, we have no idea what the position is, and vice versa. It's one or the other, or some degree of one or the other. We can never know with certainty of one, then we have zero certainty of the other. And
Gotcha.
so this has something very similar in quantum mechanics for quantum fluctuations called the energy time uncertainty principle.
So the question was that all of the quantum energy that God had, or does he still have more?
He's got a few, I guess. But that's one of the questions I wish I would have asked him, because this is one of the things I have a hard time conceptualizing. There is something called the energy time uncertainty principle, but if there's no energy, there's no time in these quantum fluctuations,
right?
I haven't wrapped that part of my brain around how this all works yet. It's fragmented. So if anybody can understand that, please let me know. And
unless you are a Platonist or Platonist, yeah. Unless you're a Platonist, and then that would work, right?
Time is actually existing regardless of any changes of the universe.
Right. Well, I think as long as there is atomic activity, then there is time. But those atoms don't have to be moving, since there's motion within the atom.
Well, I think a lot of atomic activity is based on uncertainty as well. Electrons used to be thought of this literally. I was even telling him, electrons going around a nucleus like a planet, right?
Oh yeah. I've got an old textbook.
That's crap. Half the time there's the probability space of where electron might be, and shit's popping out of existence in and out. He didn't get into it, but virtual particles literally are everywhere. Positrons, electrons.
Yeah. They make up most of the mass.
Yeah.
Well, it's humans' tendency to make a freaking Russian nesting doll out of everything, and just, yeah, Nick knows what I'm talking about, exactly what I'm talking about. Just basically taking the whole concept of the solar system and like the human eye and all these other things, and just basing them upon smaller representations of something else that composes it. Just as I really think.
Your amazing mustache is made up of your smaller even more perfect.
Yeah, supervenience.
Hairs,
Yeah,
yeah.
and all of
Fractal
those
mustache.
hairs and all of the cells that make up those hairs, they also have mustaches.
Yeah, I would have. I would have. I see. I was hoping to get into one. I happen to like the fine structure stuff. I think it's fascinating. And one of the things you learn in nuke stuff, you learn about orbitals. Obviously, Ben knows about orbitals, and you learn about like the Balmer series. You remember the Balmer series? Balmer
Yeah.
series. Okay, so Balmer series is basically a photon that's jumping from an orbital from N3 to N2, and that's in the visible light range. You have. Oh my God, I don't remember the others. Balmer's the only one I really dealt with, but you have the. Oh my God, what's the other name of the series? One starts with the L, one starts with the P, and I can't for the life of me remember them. Ben, help me out here.
It's a 2-syllable. It's like lead.
I don't know what you're talking about.
The oh my God, it's just like
Damn it.
on the tip of my tongue. There's the Balmer series, which is the visible light. There's the Lanthicide, not Lanthicide. God damn it, what is it? And then you have one that starts with a P that I never could ever remember.
Are you talking about the? Is it leptin?
No, you're gonna make me look this shit
No.
up. God
Yeah,
damn
you
it.
have to Google.
Google time. This is God. Imagine back in the day, we actually had to go to the library to look shit
Yeah,
up.
the
Right?
library. Yeah.
We didn't have
And-
this
and-
fucking right at our fingertips.
And then after you get down there, because you don't have a cell phone to call, after you walk
Lyman,
6
Jesus
miles
Christ.
down there, you notice that some other jackass checked it out.
Yeah, exactly. No, it's called the Lyman series. Lyman series is higher.
Lyman.
And yeah, Lyman. So you have Lyman, you have the Balmer, and then the Peshkin series.
Oh, okay. I think you're talking about the particles.
No,
itself,
the
or-
Balmer series is so when you look. Okay, so when you're looking at a spectrum, right? You have an absorption and you have emission spectrum. And anybody who's ever taken chemistry, which I had to take this in college, you have to do these cool experiments. What you do is you take a tube, and the tube is filled with gas.
Mhm.
And you charge, you put it through, put electric field through it,
Sure.
and it shines, right? And
neon or xenon or whatever.
exactly. And
Yeah.
by the spectral emission lines or absorption lines, depending on what you're doing, usually it's the emission lines, but or the absorption lines, unless you change it, then you have the emission lines will show just the band of the color. And if you have the absorption lines, you'll see dark lines. Right. So it'll tell you can tell by what the gas is, like a fingerprint. And there's one specific line in the Balmer series called H alpha. It's a hydrogen, right? And it's a hydrogen line that exists. It's a red line that's about 700 nanometers, like that. But this line, when you see something going away from you, it'll red shift or blue shift. Right, it'll go one way more toward the end of the spectrum, and this is because of equivalency, similar to a Doppler shift, right? But
Sure.
it's
like reacting to the electromagnetic field, right?
Well, it's funny you mentioned that because that's kind of what the fine structure is. What happens is this is the core structure. So you have like an N3 to N2 jump, and a photon will jump from one orbital to another. When an electron jumps, what does it do? It produces a photon, right? That's how it gets rid of the extra energy. Right. So that energy is in the visible light range that we can actually see. This is the greatest thing about spectrography is that we know what something is like in the sun. So when somebody says, well, how do we know what the sun's made of? Well, because of the spectral lines. It's a fingerprint. We can take a thing of hydrogen, put a electron flow through it, a current flow, and we can see it shine and look at the absorption lines. And those absorption lines, each one of those configure to a different orbital transitional state. The cool thing is that the fine structure constant is those spectral lines actually are split. Now we can manually do this. It's called the Zeemer effect, but nature does it itself. It splits the spectral lines into two separate lines. One is a spin of 1/2 and one's the 3/4. And the reason for this is really freaking cool. And hopefully I pull this out my ass. I wish Landon was here. But the reason for this is that you have a relationship between the electron and the proton that each one's charged. And when you have two charges that are interacting with respect to each other, relative motion, you have a magnetic field being produced. That magnetic field is going to have a moment, it's called, with respect to the direction of spin of the electron. So think about this. I have two charges. They're interacting, producing a magnetic field. We all know that happens. We know the field effect, and I'm sure the Hall effect, which is when you have a magnetic field going through something that conducts, it can produce a flow through it.
Right.
So you have this magnetic field being produced, but now you have this electron that's spinning, right? You have some angular momentum. and it's going to have a magnetic moment, which is the influence of what would be called a torque force. And so it's going to be having a torque in a certain direction that's going to try to align that electron parallel with that magnetic field. Now, so if it's spin up, it's going to torque one way. If it's spin down, it's going to torque the other way. And because of that, it's different energy levels that's in there. It's a very small, I don't remember the exact amount, something along the lines of like 10 to the negative 5 electron volts. It's very, very small.
Right.
But it's enough to cause two transitional states in that one state. So you have a course line of, like, say, 2p. We were talking about S before, or the orbital. In that 2p, normally you have an electron jump from, to a ground state, and it'll produce a photon. But now, because of fine structure, to spin up and spin down would be two different transitions. That fine structure constant that I've always talked about, that has to do with that. If a fine structure constant was it was a little bit different, that would affect that transitional states between those two lines in that one line.
Right.
And guess what would happen? Atoms wouldn't be able to form. You couldn't
Yeah.
have what we have now. That's why it's
Right.
fine.
Well,
they call finely tuned.
and electromagnetism, I mean, it's kind of a perpetual, ever-giving circle, because the photons that are produced as a result of it actually are the ones who transmit and change the electromagnetic field.
Yeah, the photons will interact with other things, and the reason this is important was because his whole book, Krauss's whole book, wouldn't have been possible if not for these very specific things in physics, because
Right.
of these fine structure, because of the way the universe works. This not only is an explanation for the universe, it actually mandates that the universe would actually happen given these conditions. It
Right.
could be no other way, according to quantum mechanics, is the way I read it.
Well, yeah, I mean, photons couldn't even exist if there was not if there wasn't a charged particle near it.
Yes, and also more importantly, when you have a virtual particle, remember he was talking about Hawking and radiation. I think I
Right.
mentioned it, didn't he? Okay,
Yeah.
so Hawking radiation, you have a virtual particle a pair being created. One goes into the black hole, one comes out, right, as a real particle, and you have a loss of energy to the actual black hole. But virtual particles are created all the time, as we know, but they interact with electrons in different transitional states differently, and that actually could create, if I'm not mistaken, a universe in of itself from that kind of interaction. Why that doesn't occur, why we don't see universes spontaneously coming up, that's what I don't get.
Well,
That's why I wanted to ask Krauss, but I didn't get a chance
I
to
wanted
ask
to
him.
ask him that one. That one, I
don't know the answer to that. He doesn't talk about it in his book. Matter of fact,
Well,
he doesn't even get into fine structure that much in his book. He doesn't talk about any of the elements
about multiverse theory and how, like, beyond the scope of our observable universe, there was like the potential. What was it? Well, I can't remember exactly what he was saying. I understood like 10% of everything he was talking about the whole time, because God, he's just such a smart dude. But he was talking at one point about us never being able to get there, but explaining the potentiality of us being able to know there are other universes.
Oh, because it's expanding so fast that the light
will
eventually be redshifted such that the wavelength will be greater than the size of the universe.
I mean,
those galaxies will eventually just disappear from view. They'll be gone.
Yeah. So we live in like the prime time for that.
Yeah, trillions of years from now, we won't see a star, even though they exist, but they won't see it. We won't know.
But theoretically, inside of a closed universe, whatever a point in time, in space and time, at one point is going to overlap itself at some point. So in that model, we would know eventually. I mean, hypothetically.
No, I think one, it would either be a heat death, or two, it's so far beyond our horizon that anything that does exist will be impossible to have causality with us. In other words, nothing could travel from them to us that we could actually know that it exists. There's no causal relationship because it's already moved beyond our observable horizon. It's already expanded faster than light can travel or information can travel.
Right. Well, and not to mention that we can't really document it as is anyways, just because of the vast amounts of information in one, cosmic event, which is one of the reasons that I have a problem with Hawking radiation is that, I mean, it's like the evaporation of mass, isn't it, essentially?
Well, yeah, I mean, yeah, the black hole boils away. I mean, it loses
Right.
the total net energy because the particle going in has a certain energy level. It sends the other particle out, and the total net of that system is actually making the black hole lose mass. It literally boils away. And so a small black hole, I mean, if you had a very, very small black hole, right? Because this is based on the surface area. The more surface area you have, the more
The smaller black
particles.
hole.
So if you have a very small black hole though, and you have these versatile particles being created at the boundary condition, that's going to explode. It's literally like, as far as what I've read into, it will blow the fuck up. Okay, like an
Really?
atomic explosion. Yes.
Like, it won't even have to saturate, or it just
No,
like the
because it's all
moment
that
it starts.
because it's boiling away so fast. It's just going to be a huge amount of energy released. Now,
Okay.
for a very micro small black hole, it's insignificant. But you have a golf ball sized black hole, it's pretty significant. Now,
So
I'm going to be talking to John Kroon on that, Dr. John Kroon, who's an astrophysicist.
okay.
I hopefully have a discussion with him on that very topic. He's out doing field work, but that's what I'd love to talk about black hole theory with him. We've started to, but we didn't get much into it.
Yeah, because I mean that would mean that that every black hole is decreasing in size. Well, not
No, because you might have mass going in, right? It might be heating.
Yeah, not decreasing in surface size, but decreasing in mass.
But it might be feeding, right? That might offset that.
Right, but
yes,
I mean,
every black hole. There's a point in time in the future called black hole epoch where literally all that exists is black holes, and they just boil away. This is trillions of years in the future, like epically far in the future.
Yeah, that totally blows the theory that I subscribe to, that black holes are just super saturate, and at one point when they can't contain anymore, it can only go one way, and it creates a rift in space time and creates another universe.
Well, there's a whole bunch of different models that are out there about what would happen.
And mine is right. Prove me wrong.
The big thing is that none of us be around to even say right or wrong, right? So
there's some people in the non sequitur Discord server I know that don't believe in black holes as physics has described them.
Well,
so
I don't
if I
get
wasn't
that.
worried about demonetizing Steve's channel, I would show them all a black hole.
But you're white.
Well, most of me.
So brown hole. Gotcha. So no, I don't understand that narrative. Look, I'm gonna explain this very simple because I know like Mr. Intelligent Design was there earlier. And by the way, rule of thumb: if he tells you you're wrong, you're right. If he tells you you're right, you're wrong. Keep it that way.
Yeah.
But here's the thing with black hole. What the hell else you want to call it? Okay, when we look at Sagittarius A and we look at the stars, you can actually see the change of vector, right? With the highly eccentric. God damn it, I have a speech. I cannot talk sometimes. Eccentric. I still can't say it right. What was wrong with me? It's not eccentricity.
Esoteric?
No, eccentricity.
Eccentricity. No,
it's a bad word.
I'm telling you, you don't even know the pain I had growing up.
On it now.
I think you can probably find 3 more words that would replace.
This is why I would never make a good physicist. Or doctor. I'd be
you can see the stars twice. Is the big. You can see the stars twice because the light bends around the black hole, and you can see the.
Sure.
So if it's the same star twice.
Well, we know that too. That has happened. We also see a flare up, but we also see it speed up, right? And the only thing that can cause it to speed up in this path for the eccentricity. See, I get it right there. That would be a large massive object there in a very small amount of volume.
It would have to be something creating that much warp on the
yes.
The
So
space
what do you want to call it? Look at it has an effect on mass.
And with the fact that there's something there, it's that they contend with the math behind what it means to have a 3-dimensional object like a star, like a star that goes supernova or so, whatever star turns into a black hole, and have that condense into a singularity. They contest that.
The singularity is mathematical, whatever. The sun itself, if the sun was collapsed to 2.95 kilometers. It would be a black hole. It'd be within its own Schwarzschild radius.
Right.
Has any black hole that has been created since the beginning of the universe had time to fully have we experienced the death of a black hole?
Most black holes that would never boil away. It just takes too long. But unless they're micro, like
I actually looked up just for shits and giggles how long it would take, and they said that a black hole with the mass of the sun would just the mass of the sun would take
the universe.
2 times 10 to the 67th years, which is 10 to the 57th times longer than the age of the universe.
Yeah, it's unimaginable.
Yeah.
But primordial will. I mean, they're small, right? So they're going to boil away really fast.
Wow. So apparently the evaporation for the evaporation time for the math the black hole is like 5,120 pi times g to the second power times n to the third power divided by shit, I don't know,
Something
mass
ridiculous.
cubed, mass cubed or something like that.
None of us will be around.
No,
Right.
and that's my point though, is that like
What are
the
you
universe has
talking about?
been around long
We have
enough.
eternal life. What are you talking about,
But-
Steve?
But
Yeah, that's
but
great.
a black hole with the mass of the sun, and according to what you said, I guess would have a surface area that would be too small to even it would explode, right, Steve? Is that what you're saying, or would it have to be smaller?
Yeah,
than
no, I
that?
think it released energy so quickly that it would be essentially
Okay.
a gamma ray explosion.
So,
It would just-
so even if that black hole could exist, there still has not been enough time for the universe to be around for that black hole to have evaporated. So I mean that's a long. I mean we're talking like
time.
we're talking like 10 with 57 zeros behind it. That's how much longer it would take than the current age of the universe.
Yep.
That's insane.
Now, I mean, again, you got to remember, like even like the sun, you got to remember putting that much space in the size of 3 kilometers is pretty impressive. That much mass in 3 kilometers. Now that'd be not a lot of surface area. I mean, I think that would boil away much quicker, obviously, than a supermassive black hole like Sagittarius A. That would take, like you said, 10 to the 60, 70, 80, just ridiculous amount of time.
So with
Sun,
the
I don't think it would
Hawking
be that long.
with the Hawking radiation, keeping in mind the second law of thermodynamics, where does all of that expended energy and mass go? I mean, what part of it stays within the black hole, and how does it decrease in size if it's not losing all of it?
Well, what do you mean? It would decrease in size because it's losing mass.
Right, but it only gains that mass because it rapidly intakes it.
But if it's not feeding off anything, there's no mass going into that, right? It's just boiling away. You're losing energy out of it. Again, there's only 3 things that are conserved with a black hole: angular momentum, charge, and mass. So now you have a situation where you have real particles being spewed out of it, right, from the boundary conditions, which is your Hawking radiation. And now you have this massive mass particle. I mean, what's going to happen when that black hole is no longer massive enough to be a black hole?
Exactly. Well, I mean, but how massive is a black hole? That's the thing. I mean, how long does it go? We know that they're conical, and at some point there is a saturation point. We don't know what happens at that saturation point, but I mean, Hawking radiation.
I don't think we have any idea what happens at that point. I don't think we've ever seen a black hole evaporate, and we would have no clue.
Well, yeah. Well, we can. We have evidence for Hawking radiation. We have evidence for things.
Sure, but we've never seen a black hole actually evaporate to the point where it's gone. We wouldn't. I don't think we even modeled that.
What I'm saying is, like, have we modeled the intake of mass into the black hole, like whatever it's sucking in, like whatever particles and light and matter that it's sucking in, and have we done a test of intake versus output?
I have no idea. Landon, where's Landon?
Because both are observable, right? We don't know how much is already in there, but we know how rapidly things are going
Well, we
in.
do know how much. No, we can measure the mass of the black hole. We can see its influence on things.
I mean, yeah. I mean, yeah. We can see relatively I'm sorry, I'm spacing on your name. Let me hover over it. Nick. I'm sorry, Nick. That Nick was saying, that we can see the same star twice, due to the curvature of space-time, due to a large mass warping our perception of space-time. But I mean, can we accurately say that all of that mass is because of what is in the black hole and not any part of the black hole itself?
I'm not sure what you mean by that. I mean,
It doesn't seem like there's a distinction between the black hole itself and how much mass is in the black hole.
Yeah, I don't think I don't even think
Right.
it makes sense to say in the black hole anymore.
So once a black hole happens, once the stars collapse and once it is created, the black hole, so to speak, is any part of that black hole part of the original matter, or at the moment of creation does it begin with zero mass?
Well, no, it takes. You have to have, in order to create a black hole, you have to have a certain amount of mass within a certain
Right.
confine, the Schwarzschild radius, right?
Right.
And so
with a certain amount of pressure. I mean, a certain amount of not
it's
pressure.
It's just volume. It's just basically it has to be dense enough. That's all it really is. I mean,
right.
if you took the sun and you just compactified it and just compressed it and compressed it
Sure.
and compressed it, eventually it would form a black hole.
Right, because it basically implodes upon itself, and
well, it doesn't. It's not even an implosion. It's within its own event horizon. That's what the Schwarzschild actually is.
Right.
There's something called a matter wave, de Broglie waves. Okay, and this could be working for the macroscopic cross section, or excuse me, macroscopic universe. That
Okay.
if something is within its own matter wave, it will form quantum mechanical effects. The
Okay.
analog to that is the Schwarzschild's radius. If something's within the Schwarzschild radius, it will form a black hole.
Okay, so after running this through my own head,
And the other one is called the
black hole.
Go ahead.
A black hole has to have mass at the point of creation, or else it wouldn't have the effect on space-time without that mass.
Yes, because
Yes.
it's the density.
Okay, so it just uses all of the mass from whatever whatever stellar object that it's condensed of or consisted of.
My phone has a Schwarzschild radius. It's like probably on the order of
As
like
an atom,
angstrom.
photon.
Yeah,
Right.
Yeah.
Sub-angstrom levels. But if
Yeah.
you take all the mass in my phone and you took it to some amount of radius such that you had your mass divided by volume for your
Sure.
density, that would eventually my phone could be a black hole, and then this
Exactly.
But
Now, there's also other limits too.
But what I'm saying is that if you were to take the mass of your phone and you were to take the mass of your black hole at right at the time of the event, the transition, would the mass be the same?
the phone becomes a black hole.
Okay, so
Gravitational well is different from what's at the bottom of that gravitational well, right? The
Right.
thing at the bottom of that gravitational well is the black hole. The gravitational well around that is like the event horizon. Or,
Right. Yeah. So yeah, you have the compressed. I don't want to call it a singularity, but a compressed. Right. And it's creating a wrinkle or a dip, so to speak, in space time. So the actual dip itself is not the matter, but what's at the bottom is the matter.
yes.
There's nothing
right.
But I think the problem is that you can't think of a black hole in 3D and past the event horizon. It doesn't really work that way any longer.
I mean, you can kind of. I mean,
I don't think
you
it
can
makes sense to do
conceptualize it.
It's like an asymptote. Like what's tangent of pi over 2?
But I mean, that's a good point. But I mean, the model though of the trumpet bell, like the trumpet horn, and then the condensing down, to the strongest mass point, or the strongest strongest point of mass right there. I don't know. Something that's always bothered me is like you see these big black holes, and I can't help but wonder, like, we witness space and time, like the fabric of space and time being ripped all the time, like with the Twitter analogy that was sent. So I mean, at what point and at any point are black holes capable of ripping space time just because of the sheer force that they put on it?
I don't think they can rip space time. I don't think that's going to be what's causing like a big rip.
They're specifically having an effect on space-time due to the nature of how space-time interacts with regards to how gravity works in order to produce a black hole to begin with. You can't break the system because it's within the system.
Yeah, the only thing that I think
what would a rip
would be
mean? Yeah.
Well, there's something that's called vacuum decay. Vacuum decay theoretically could do what you're describing, Jim, and vacuum decay, if it happened, would suck. It would suck. The universe would literally just cease to be.
That eventually puts like a never-ending bag on your vacuum cleaner, right? And it's just
but there are some other limits that you might be aware of. Ever heard of the Chandrasekhar limit for white holes? White dwarfs. So what happens is a star can form a white dwarf, and a white dwarf is held up like what's called electron degenerative pressure. That limit, the Chandrasekhar limit, is if a certain amount of mass within a certain amount of area, it doesn't form a black hole, it forms a white dwarf. And so it's held up because of Pauli's exclusion principle. Electrons are so compactified, they cannot be in the same orbitals because, again, exclusion principle, it forms this white dwarf. But if you compress it even further, okay, it has what's called the TOV limit, Tolman Oppenheimer Voloff limit, and that will cause the electrons to literally combine with the protons to form neutrons, right? And then neutrons, if you have a star that's comprised literally just of neutrons, or mostly comprised of neutrons, I guess there's some other things in there. But what do you call a star that's comprised mostly of neutrons and actually acts quantum mechanically as a neutron?
A neutrino.
No, a neutron star, dumbass.
Yeah,
Okay,
I know.
okay.
I know.
Yeah, I know. But yeah, so that's how a neutron star forms. It's compactified even further. And then if you go in further than that, then you get within the short charge limits, and then you form a black hole. That's kind of the way to think about it. So each step, you're forming a different object, and you're compactifying it more and more.
Well, then that clears it up. I've decided black holes aren't real.
Clearly.
Well,
Oh God.
Science.
they're God. They're
Science,
God.
yeah.
I think that's it. There's no evidence for them, and okay.
Every God built a black hole.
Granted, every God concept I've been presented with sucks. So I mean,
Out of black holes.
Yeah, what's wrong with that, man?
And are
Black
they
hole.
actually holes,
This
or are they got an
They're not
exit and
holes.
an entry?
well, and,
Look
and every God belief you get in is pretty hard to get out of.
This universe is fine-tuned for black holes. Therefore, the God of black hole makes sense.
I actually,
Oh.
I have it.
I am now converted. Thank you, Steve.
Black hole God.
I have.
That doesn't
I'm
sound
going to
right.
meme that. Yeah.
And I also think Steve, as the Pope of agnosticism, should also be the prophet for the black hole God.
I don't want to be in charge of black holes.
Yeah.
You're not in charge. You're just a prophet. You're just supposed to tell us about it.
So speaking of those, so have you guys been following the dialogue I've had with Richard Carrier on his page? It's epic.
I
haven't.
have. I'll be honest with you. I read the first two back and forth, and then I was like, "This is
I'm kicking his ass.
really."
I'm kicking his ass. Admit
I've-
it.
Yeah, and he's just ignoring your good points, and he's just
Right?
doubling down on his bad points.
Dude, thank you. I thought everybody's read that. It was like, what the hell's going on here? But people that know on the Facebook page, Dr. Carrier's Facebook page, he set up a 1v1 court thing for him and I. Just him and I. Nobody else can leave a comment. He'll erase it, which is fine. And I've answered every one of his questions easily. I've addressed them as the best as possible. I've tried to meeting of the minds kind of thing. But every so often, like 4 or 5 times he's gone on this weird tangent of things that I'm not arguing, and yet he's arguing against something I'm not arguing, and kind of implying, Steve, you know, that's really bizarre that you think that way. Well, no, I don't. What the hell? I don't. I'm really confused here. But it's fun. I like Richard, but damn, it's he. Does he even read my comments, dude? I mean, I don't know what he's responding to.
No, he doesn't. The problem is, and I don't care who knows this. It's a big problem in the atheist community. Aaron Ra's guilty of it. Richard Dawkins is guilty of it. Richard Carrier is very guilty of it. Is these people have built their platforms on an idea that they later find to be flawed, and they can't do anything about it because they have so much invested in these bad ideas that they can't back out of it without losing a significant portion of their following.
No, I couldn't agree with you more. I see that all the time.
Yeah, it doesn't mean that, you know, they're not capable of having their mind changed. And
No,
then,
Right. No, I
true.
agree, but it does mean that they're wrong.
But foundationally, it's much harder to when you're a coherentist theorist, and Nick can kind of chime in. A coherentist can take planks from their what's called the raft of beliefs, and if you move one plank, you can replace it with another and move things around. You don't destroy the raft. But a foundationalist like myself, our foundational beliefs, you're not open for revision. You can't go back and say, you know what, I'm going to get rid of that property based belief. It doesn't work that way. You have to reformulate your entire system at that point. And so
Steve will destroy his raft and drown.
What's called pyramid versus raft. So pyramid would be foundationalism, raft would be coherentism. That's how Sousa describes it in a paper called The Raft and the Pyramid.
I thought one was built on the back of other people and the other one you did yourself.
We call that American atheist.
Oh, shots fired.
Got 'em.
Shots
So
fired.
they make a good point though when it comes to, like, you know, they have so much invested now. You know, when you have Aaron, God bless his soul, and I do love Aaron, but when Aaron props up,
he's great. I love him.
when Aaron props up somebody like Nate Brody as his go-to philosophy person and saying, "Oh, look, this guy has this shadow over Steve's arguments. Go watch him." I'm like, dude, you might as well just send somebody answers in Genesis. Okay, at that point, you're so far out of the
Jesus.
realm of philosophy and
Oh.
any kind of rational.
Oh, that
God.
hurts.
Oh yeah, I mean,
Yeah.
Nate's videos are just shit. I mean, just straight up crap. He does it for exploitation. He does it to get views. He admits it. He's a troller. He'll admit he'll have clickbait. He does. That's all he does. And so I don't even bother with him because it's like, dude, you're not even talking about my argument. Go whatever. But Aaron, I swear to God, Aaron takes this guy seriously, and yet he won't take actual philosophers, literally people with PhDs, that telling him no, that it doesn't work like that. Aaron, he'll do it for biology. He'll do it for sciences, but no, for philosophy. No, I'm going to go to this lawyer guy who's arguing like a lawyer.
Well,
That's
here's the
fabricating
thing.
shit, and he's going to be the defeater of Steve. And by the way, no, literally, this is public because he put it on my Facebook page. Aaron said that I was in damage control mode because of what Nate put out. I was like, oh, for fuck's sake. I was like, there's no damage control to be had here. He's
just wanna
fundamentally
make
practically wrong as any creationist I've ever seen. That's
I want to
what-
make a quick comment.
Oh
on
God.
this. So,
Hilarious.
I know that Aaron doesn't really like philosophy, and what he told me was because he's only ever seen it misused.
And he's
So
and he's told me the same thing. Yeah.
Yeah.
Yeah. No, and he has a good point, but even when he sees it misused, there are sometimes he just doesn't grasp the concepts. I mean, he doesn't understand fact and theory. He still doesn't get Hume's problem of induction. He thinks Hume's problem of induction has to do with the fact that induction doesn't prove anything conclusively. That's not Hume's problem of induction. Okay, so he just has
But that's how he understands it.
what?
But that's how he understands it, and that's all that
But
matters.
that's not what it is.
Yeah, I
Hume's
know.
problem with induction has to do with justification to use induction without using induction, because you cannot deductively prove induction, and you can't use induction to use induction, and you can't even go so far to say the uniformity of nature is going to be the always way it is by induction without being circular.
Well, that won't
That's
stop people from doing it.
but it's still circular.
Yeah. So somebody in the live chat made a really, really good point, going back to black holes, saying that we don't have any evidence of black holes before NASA said we had black holes.
Because we
Therefore,
did observations, and they said, "Oh, look."
Trolls.
Well, first of all, we did. They were predicted. Matter of fact, Einstein predicted these things. Equations say mathematically.
yeah, but he didn't see one.
Right,
I mean,
but then we said, "Oh,
Oh,
look, here's a reason of space. It's having this effect on this star that has this much mass. In order to do that, you need this much mass to do it because of physics. We understand that, and it's in this small amount of space. And guess what? There's nothing coming from it. There's no light. There's no energy. There's nothing that we can detect from it. It's
Yeah.
a black hole. Oh,
Well-
hang on. We can detect X-rays because of what happens around the perimeter. You have the photosphere that's being produced, and we can
Right.
we can detect things from the accretion disk. But if it's not feeding, they're invisible.
but that was from induction, Steve.
Yeah, well, we can use induction. Not the problem with Hume doesn't say we can't use induction. We use induction all the time. You just are not justified to use it. That's the problem. How do you justify the use of induction?
Yeah. Well, and that's probably why Aaron doesn't like philosophy. I think you have to have a certain mind to like philosophy. I got my degrees in
What do you know?
philosophy.
You're just a philosopher.
Yeah, I know. I got my degrees in philosophy and psychology. My wife calls them degrees in bullshit and mind fucking, and she's
my God,
right.
that's what Ruben is going for too. Great.
I got a
And I met plenty of extraordinarily smart people who just get into philosophy and just go and then it's the same thing with law too. You have to have a certain mind for law, and that's another type of mind fucking. I put the thing up, your thing with Carrier up on chat.
Wow.
Yeah, I put it up on the chat
Crazy.
here. Thing with Carrier. I wanted to take a better look at it, but it's another thing to note.
Please do. I'm interested.
Dr. Carrier is not a doctor of philosophy. He's a doctor of ancient history, which is just worth noting.
He's so fun.
Yeah, no, he's good at philosophy. He clearly knows what he's doing. He's not a, but I just thought it was worth noting.
Well, let me know what you think about it. Read the dialogue and give me your impression of it as well, because other people have as well. But real quick, I was going to say, God damn it.
All right, well, what do you think of that? Carrier, I know that he concentrates a lot on like history of philosophy.
Well, and well, I just brought it up because you had said he had referenced other somebody else, but you haven't found a doctor of philosophy who disagrees with you, I think is what you had been trying to say.
Well, he doesn't. Well,
And
Krauss
we will only go back to the Greek classics. He won't go back further than that.
Kerry doesn't really disagree with me on much. What I meant, what I was saying was, I haven't found a philosopher that disagrees with me on the usage of my terminology, with no atheist agnostic things as it relates to philosophy. Not one, nobody.
Okay.
Now there might be some out there that say yes, Steve's uses is very congruent with the philosophy, but we would like to change it to this. That's a different argument. Now I haven't really seen that. Maybe the only proof, obviously you have Bullivant, you have Martin, you have Smith, and you have Flew arguing those things. But even in Flew's paper, he specifically points out this is what atheism means. It means the belief that God doesn't exist. This is how the word has been inferred in the literature for hundreds of years. He wanted to change it. Right? Martin wanted to change this. Bullivant wanted to change it. Someone wanted to change it. These are people that want to change things. Now, I'm not against change, but there needs to be a rational reason for the change. There needs to be a good reason other than political motivation. That's not a good reason for me. But anyways, yeah, Kerry and I don't disagree on a lot. He actually agrees atheists have a burden of proof. Amazing.
Yeah.
He acts, and all of them, not just a lack of belief atheist. I mean, not just a atheist believes. He says that yes, if you deny a proposition, you say, hey, I don't think that is true. You need to give reasons. That's a burden. Fair enough. And he doesn't disagree that of course atheism is the way I use it is correct, and agnosticism. His argument is basically really weird, dealing with probabilities. That the way I'm reading it, and please read it and let me know what you think. But I've talked to somebody else on this who reads it the same way, so I think it's more than just my inability to understand. But he seems to be arguing that if something has a 0% chance or greater, it is believed.
Wait, 0 or
No.
everything has 0 or greater.
No.
Well, it should be greater than 0. You're right. Yeah, greater than 0.
Greater than 0.
Non-zero.
Okay.
Non-zero.
No, I would say that that's inaccurate. I mean, because it's all. I mean, belief is dependent on personal justification.
Yeah,
Well,
that's what I'm saying. It's a little bit weird what he's arguing. Maybe I'm just not reading it right, but he's using terms like certainty and conviction and some other terms. And
I mean,
let me hear Steve finish, because I just want to quickly get Steve's take on what Kerry's position is, because that would be a huge help.
that's the thing. I'm not quite sure. He breaks it down probabilistically, and yet I'm trying to explain. Look, if you're 51% convinced, right? That doesn't mean that you're convinced. It means that you're on your way to being convinced. There's a certain amount of threshold, which is arbitrary. Call whatever line of demarcation you want. Then you're actually convinced, right? You're not. You can have leanings one way or the other. That's not a big deal. But you're not exactly convinced until whatever that threshold is that meets your justification to say, I'm now convinced, whether it be 60, 65, 70%. And that's easily explained with the deck of cards. You have 52 cards, shuffle them. If I show you top card and it's black, you're not going to say, I'm justified now to believe the next card's red, even though it's slightly greater chance. You're still guessing it at that point. Just because there's a higher probability over 50% does not make it justified to hold that belief. And that's what I'm arguing to him. And I think we're not meeting in the minds there. But
there is something to be said if you, instead of having 52 cards, if you only have 3 cards and you are shown that two of
then you're
them,
66% then.
Yeah. So, but if you're shown 2 of them are black and one of them's red, and then you get shown the first 2 cards and they're both black, I guess that's actually just a distinction of knowledge on the ontology for that.
Yeah, unless it's the Monty Hall problem. If the Monty Hall problem, they show you one, and you want to be able to switch, then you're at 2/3.
Anyway, I actually have work tomorrow, so I was going to.
I'm going to go eat. I'm going to make some pizza. This was a long day, but that was a great hangout.
It was a great hangout, and you know what? Great job getting Krauss on to both you and Kyle. That was awesome.
Congratulations.
Awesome job.
And I got to tell you, I think that should could have gone better. I think it was flawless.
Awesome.
Anyway, Steve, I want to talk to you some more sometime if we can set up a hangout or something about the difference between multiverse stuff and possible world theory, because I still want to hash that out with you, because I think that we're talking past each other a little bit on Twitter, and I know Twitter.
Be happy to. I'm actually in April. I'm going to be having Dr. Graham Priest join us.
I was going to ask you about that too. That professor for modal logic, right?
Yeah, so I'm going to get back with him, but possible worlds and multi-world are completely and utterly distinctly different things. They're not even related.
Yeah. So anyway,
What do you think we disagree then? If we
well, I think on Twitter we've just been talking past each other a little bit with regards to
It's
like
Twitter.
I'm talking about multiverse theory, and you're like, oh, but philosophically, there's only
Oh,
one.
no, I get it.
universe.
No, I don't think. I honestly don't think we disagree, but we'll have a hangout on it, sure. But
Absolutely no,
I
no,
definitely
because
think that you're just talking science. I'm talking philosophy, and that's fine.
right.
See, I just
Well,
think it's
but-
because
but-
Steve has his own language.
Yeah.
Oh,
well,
no.
no. The rule of thumb is if you're on Twitter, you're an idiot to me. So
Right. No.
Twitter, Steve.
Mhm.
People think. I swear to God, people think I get so upset on Twitter. I'm like, dude, you don't even know. I don't even care on Twitter. I use it as a testing ground. I use it to run arguments. I use it to engage with people, and I'm happy to explain to people. But if I find out you're an idiot and you're just there to argue, you're not going to get much out of me. It's just,
All right, cool beans.
so, and you're not, obviously. I'm giving you shit.
Aw, thanks,
Now,
Steve.
Nick, that guy Nick, that philosopher dude. Oh, for fuck's sake.
You didn't leave yet.
Oh shit! God damn it!
Wait, who?
You're supposed to warn me of these things. Yeah. But anyway, so any other than dealing with the Lawrence Krauss, any other last words? Anything where they want to plug? I appreciate you guys. 130 people watching late this night. This is pretty good actually.
Nice,
Late at night.
nice.
Usually only get that in the mornings. So, but I love all the people that come over from the after shows. I want to start having more often them. I think they're fun to kind of continue the dialogue. And I think you guys have an interest in it as well. And like I said, take for a grain of salt, which was put out in this video. We didn't have a real physicist in here to validate or verify the information. I usually say I'm about 80% there. I'm okay with that. The rest can be corrected.
80%? That's pretty confident. That's pretty high.
I'm just going off of what I.
I'm
just going off of what I remember from when I was like really into
how about
into
75%
physics.
then maybe?
Ben says that he has work tomorrow, but he looks like he just like popped a couple mollies and is waiting for everybody else to leave.
Yeah,
I do have work tomorrow. I need to sleep. What do you think all these are for?
So what is actually your? I mean, I know it's you deal a lot with physics, but what actually is your thing? I thought it was computer science, Ben.
No. My well, I mean, my thing is my education is in ceramic engineering. It's a subset of material science that deals with specifically non-metallic, non-organic things.
Sure.
Yes, I have friends that make toilets. I don't make toilets.
I was just gonna ask if
You know all about
make
porcelain.
I do actually. We can have an
porcelain?
entire conversation about all my educational background. Long story short, I like
you know what Young's
electronics.
modulus is because Mr. Intelligent Design claimed to be a civil engineer, and he had no idea what Young's modulus was.
Yeah, I do know what Young's modulus. I also know the difference between strength, fracture toughness, and hardness, and all of that. So
Brittle fracture and plastic deformation. Yeah, I took metallurgy too. Yay, good job.
yeah, no, I have good metallurgy friends, but no,
I hate
ceramics
that
are.
topic, but yeah,
Nice.
Yeah, so
ceramics gonna be the wave of the future, man. I mean,
no,
totally.
absolutely they are. The reason why we're going to have quantum computing is due to like advancements in material science. That's it.
Right. Well, we should definitely do a hangout on material science because I'm really fascinated with that as well.
Oh, so if you want to know the stuff that I love the most, it's electronics and specifically like energy storage technologies. I love batteries. I love electronics. Right now, I'm making my way into the avionics field, so I'm really enjoying just some basically just electrical engineering
It's funny you
stuff.
mentioned that because I used to be a store manager for Radio Shack, and I watched the development of batteries. You start off with like a zinc and a magnesium dioxide battery, right? Carbon, magnesium dioxide, zinc, and then you moved into these more sophisticated things using acids, and then you moved into nickel metal hydride and lithium ion and all these different. Yeah. So now the most current thing is these hydrogen cells, these 4th and 5th generation hydrogen cells.
You mean like solid, like fuel cells?
They're fuel cells. They're hydrogen fuel cells. Yeah.
Well, I mean, most of the advancement I'm familiar with in terms of like the stuff that they've been really pushing for in terms of commercial and industrial use is solid oxide fuel cells, which I have a professor, Dr. Dogan, who I was taught under. Pretty much ceramic engineering is like a 3rd generation science now. Like I'm learning from the people who learned from the people who started ceramic engineering.
That's crazy. And in like 20 years, Ben, you're gonna you're probably gonna make like the first flying toilet or something that nobody else.
That's what we need.
I would much prefer room temperature superconductor, but that's
so
Thank you.
somebody can say, "I don't give a flying shit," and Ben be like, "I do."
Can you imagine? Can you imagine that what would happen if we actually had the ability to produce superconducting materials at room temperature?
Oh my god!
How we would. I mean, think how much less loss we have. How much computing power we can do. We'd have no losses. We have.
I have something. I have
Energy
something that
would
I
just
need
be
to grab
would be
real quick.
so cheap it'd be ridiculous.
I'm gonna
I
show and tell.
I can grab before I head to bed for y'all. It'll be a treat. Let me just.
Oh, okay. Last time a guy said he was gonna grab something before we went to bed, I had to like delete that video.
He did say he was going to show us that he knows the difference between hardness and
Yeah, this goes to this video.
and toughness, and what was the other one?
Well, I don't know, brittle fracture.
Oh, jeez.
Plastic deformation.
I was reading about some ceramic technology into automotive to do with engines or petrol engines or whatever.
As long as you're not using spark plugs, because I hate ceramic
Well,
spark
think
plugs.
about it. They could make a plastic engine that could withstand the heat with the high enough ceramics. When you want to have it'd be a lot less weight compared to what for stainless steel.
Yeah.
Well, yeah, but you also have a lot
engine.
of pressure. You also have a lot of compression to deal with, a lot of internal pressure, and then you have to do with consistencies with heat and cold, and worry about contraction and
Thermal effects. Yeah, I mean that's one of the biggest thing with buildings and things like that. Thermal expansion and contraction.
Well, I think they're starting to make roads. They're starting to make roads, if I recall, out of ceramic material too, because ceramics are a lot more recyclable than a lot of.
Roads have always been made of ceramics. Bricks are ceramics. Just saying. But no, I was trying to find my superconducting pellet, and I can't find it.
This is true. A superconducting pellet.
I have yttrium. So what I have a small thing that I made myself in lab. It's Y123 or yttrium barium copper oxide. It's a high temperature superconductor that is superconducting at liquid nitrogen temperatures.
Right, and you get more on the quantum level. You get better computing at those lower temperatures because you get better conduction, right?
Well, so there's two types of superconductivity, right? There's the standard superconductor, which is a metal usually at like singular digit Kelvin scales. I think at highest you can get maybe like 12 Kelvin superconductivity.
That was like 9 or something.
Yeah. At highest, you can maybe get 12 degrees Kelvin. That's 12 degrees above absolute zero. But with type 2 superconductors, you have quantum pinning of the field line. So you have some permeation through the material itself, but it's pinned into essentially a singularity of all the field lines and everything. It's super cool. Super complicated, and I can't find my pellet.
I'm way out of my depths on that one, man. I love that kind of stuff. I love learning about stuff I've never heard of before. To me, that's like the coolest shit. I have no idea what the fuck he's talking about. And
Steve,
I can
hit me up anytime on the weekends, and we'll have a hangout or something if you want to talk material science.
Well, and what sucks is like things like chemistry and physics really bored me. So like I really bypassed chemistry and physics like in my own personal studies, but like I'm so passionate about quantum computing and I love learning about it, but it's so hard because I bypassed physics. But at the same time, I feel like I'm learning a lot of my physics just because I am so passionate about quantum computing that I'm learning it putting the cart before the horse. But
my education, I feel, was so valuable to me because it was so hands-on. The very first thing that we were learning about for materials was mud lab. We made pots and we
like clay,
literally clay porcelain bodies and such, that because you learn different properties that those have, you start learning a feel for how those traditional ceramics work, and they're still important.
So
then you start looking at glass, and then you start learning about crystallography a little bit more, and you start learning the structure between how interrelated atoms work in ionic bonding and shit. It's just fucking amazing.
Right. We learned about what we call crystal lattice point defects.
Yes.
And obviously ionic covariant. But yeah, the intermolecular things are fascinating when you have point defects and you have capturing of certain particles in a defect. But it's very prevalent in something I was talking about when it came to these things called perchloric halos, also known as polonium halos at Gentry. So I did a whole presentation on that, and actually a lot of this involves a lot of things like that when you have interstitial point defects. But let me ask you this, and then we're going to end this. But suppose you have a reactor plant, right? Because I work on reactors.
Yeah.
And this reactor's made out of whatever material. I don't heat that material up properly. I don't thermalize it to I get an even distribution of the material. And all of a sudden I'm at operating temperature and pressure like that. Well, or worse, I don't cool it down properly. So if I have a very hot system and I cool it, I introduced very cold water to that system.
Yes.
What's going to happen in that system?
Because for the most part, shielding on like nuclear reactors and that sort is either going to be some layered metallic compound or a ceramic compound. If it's metal, you have a good chance of it not completely fracturing, but at the temperatures that they operate at, and if you try and cool it and quench it essentially down, it's going to turn into little tiny bits of cracked whatever it's made of.
It's the brittle fracture.
And at best, you're going to have severe warping.
So this is where the difference between so if you have
plastic deformation, it's not going to be plastic deformation. That's
no, not the same thing, but on a molecular level.
No, we're talking about completely different things here, Jim.
So what you might be thinking about is the ductility that metals possess. So if you look at the stress strain diagrams, right?
Exactly.
You have a certain period where you apply stress onto it, and it has a linear section there, and then there's a rounded point there. And if that's your maximum strain there, if you're a metal, you'll reach that point and then dip down a little bit, it depends on the properties of the metal specifically and the alloy and yada yada. But with the metal, you have some stretch to it where you can actually look this up with the dog bone stress strain. For stress strain curve calculations to actually perform the test, they make little dog bone shaped pieces so you can tug on them from both the top and the bottom, and you can see the necking that occurs, and you can pause the test and see that necking and that ductility in the thing.
The tensile strength of it, is that what you're saying?
Yeah, it's related to that. But when you have
what you're basically doing is you're seeing if the material is going to go back to its original position. If it's past the critical line, and it has plastic deformation, it'll never go back.
Slip planes. That's what it is. So if you have your metal in a certain orientation crystallographically, if you have a single crystal of that metal essentially where it's nice and even homogeneously there, you'll create slip planes, and these slip planes are the actual planes of atoms because it's all just stacked cubes.
Yes, exactly.
Cube lattices.
Right.
With slide past one another.
Are they inward-facing surfaces in that structure? Not for metals. Metals are simple cubes. You have four atoms on top.
It's very basic lattice.
But by like something like table salt that would be.
That's ionic bonds, though. So here's the thing: the difference between the ionic bonds there is that the reason the slip planes function is that you can essentially imagine you've got two cubes right here. They're joined face to face. But if you have the slip plane, if it actually slips and that causes the ductility of it, you can shift and you can have them, instead of being face to face, edge to edge or corner to corner, even corner to corner on the diagonal there. And because it's a metallic bonding and it's just shared electrons, it doesn't matter. It's still just there. You've altered the position of those atoms, but functionally the metal is still there. It still has some strength inherent to the material. Ionic bonds don't work like that. They take a lot more energy to do so. They're a lot more brittle as a result.
Yeah, and the reason I mentioned that is because a couple of weeks ago I did a stupid thing. I actually had something brittle fracture on me. I was baking something in a Pyrex dish, and I wasn't even thinking. I put it out. I put it in the sink, and I just turned on the water.
Oh yeah.
I mean, I've done that baking bread.
Don't do that. And I should have known better, right? I mean, I operated nuclear power plants. I understand the concept of brittle fracture. Now you have to literally warm up the system, and you have to thermalize it. You have to cool it down properly. I've done hydrostatic testing, and yet I did something incredibly stupid.
Hot water, yes, but not cold water.
Pyrex is super fun because it used to be better than it is now. The current composition of Pyrex is just a different sort of variant on the soda lime, or it used to be constructed with a sphenoidal decomposition glass, which is where you have a borosilicate glass, so it's got boron tetrahedrons in there, and you're still got a silicate glass former base in there, and then that's acidically leached out and washed out, so then it remains this complicated network of silicate glass, pure silica glass, essentially, and that makes it super high in melting temperature, super strong with regards to its properties due to the structure of the amorphous macrostructure alongside of the spinel decomposition there. Super great stuff. But they stopped making that in like, I don't know, 1950 or 60 or something. So all Pyrex ware after that has become garbage.
So,
Well, I mean, glass
I had,
itself is that's an amorphous solid to begin with, right?
Correct, yes.
Yeah.
But there's a lot of complexity to amorphous solids. You can have plastics are technically amorphous.
So I used to live in Utah, and I lived in a log cabin that was built as a way station for the Pony Express, and I had no electricity, and the only running water that I had was gravity fed from from higher up the mountain for me. I was at 6,000 elevation on Mount Moriah, and it was a little bit higher above me. So I only had gravity fed water, no electricity, but I had a wood burning stove that people call them a Franklin stove. Mm-hmm. And I had learned to make bread in it, and by putting the fire onto one side, and I used Pyrex. But in order to bake bread, I had to get the temperature down below what I would normally keep it at for heating the house in the dead of winter, and so I would have to sacrifice some of my heat in the house to make bread. And so I'd get the fire down low, get some good coals going, and move everything over the side, or I'd put it in a horseshoe and then put the bread in the middle. And closed it up, and I waited and went and I took it out when it was done. It was some great wheat bread, but the thing is that it had cooled down so much in the house, it was probably in the single digits if it wasn't below zero. And I pulled it out and I set it on the counter, and I turned around, and it was like a fucking grenade went off. Boom! I didn't put it in the refrigerator, nothing like that. It was just the rapid change. But I think it was the old Pyrex, because it was my grandma's Pyrex, and I've had Pyrex explode on me recently. But it's like
you don't want to put it on a cold surface.
It's like the bond.
And the other thing is, and then I gotta go. But if you read his book, by the way, he meant this will come full circle because Krauss mentions in his book. When he talks about beer, like really, really cold beer. And it's past point of saturation, super saturated. So the fact that when you release that pressure, it actually freezes solid and it shatters the glass. It's another thing to be aware of. You have a phase transition, and so you have this fluid that's under pressure, carbonated fluid, and it likes to be the lowest ground state. And that particular ground state is going to be liquid, but as soon as you release that pressure, the ground state it wants to be in is solid. Well, solid takes up more space than liquid, for beer at least, and that shatters the glass. So you got to be real careful when you're working with certain things, with certain materials and certain temperatures, and each one has different properties. Some materials have a different way different properties than other materials, even when it comes to like electrical properties. Some of them will actually conduct better at higher temperatures, some conduct worse, some bend more. When we used to have these things called thermocouples, and what the thermocouple does, it detects the temperature in the reactor at a certain point in the reactor, and the way it works is it has two different types of metals, and they will, when they heat up at differently, so they bend differently. So when they start bending out, you can make a measurement, and that'll tell you what the temperature is.
Not exactly correct, Steve. It's called the Seebeck effect. There's actually an electrical effect that occurs.
Is that what it is?
Temperatures. Yeah. So the two different metals will have different.
I didn't remember that, to be honest with you.
Yeah.
I'm going to take your word for that.
Yeah. Seebeck effect. Look it up.
No, I believe you. Dude, I may have learned that back then. I may have not. I was 30 years ago, so possibly, but I'm not going to doubt you on it. I know the effects, I know, but what's it called? Seebeck effect?
Seebeck,
I don't remember that, but I'll take your word for it.
It's like SIEI or some SIEBECK.
All right, cool.
All
right, well, there you go. We all learned something tonight, and I'm going to bed. Actually, I'm going to eat food.
I'm going to party and then die tomorrow, I guess.
This was a long night. Thank you guys for watching. Nick,
it was great talking to everybody. Thanks for putting up with my ignorance.
I don't mind.
You're amazing.
I'm only learning.
All right, and Seebeck. Okay, you know what? Seebeck. SEEBCK. That does look familiar now.
Mm-hmm.
Yeah, I'm lucky I remember the Zemer effect. But anyways, I'm gonna go. I'm just babbling. Night.